Welcome everyone to Barcelona for those who came from abroad. Good morning. I will try to explain two main ideas through a long presentation with a long introduction also. And these ideas were developed by this team. It was a collaboration between Alba, Ferran Rufat, Guillermo Casas, Miguel Santasusana, and Professor Oñate about the bonded DEM. And the story starts 6 years ago in Denver, Colorado. It was the DEM6 conference, and I attended a plenary talk by Professor Feng about the fundamental issues of discrete element, about particulate and continuous solids. And funny thing is that he dedicated like more than half an hour to talk about granular, particular discrete systems, and he explained a lot of interesting things about that. But when he reached the part when he was talking about continuum mechanics, that's the part which is solved by what we say the bonded DEM, he wrote a big question mark. And he didn't talk much about that, just trying to say that there was many things to be developed there. At that time, we were trying to implement the bonded DEM in SIMNE. What is the bonded DEM? Basically, you have the standard DEM with this typical model with normal spring, tangential spring, some dampers, you have friction, but you have also this, what we call the bond, which actuates in tension as well, not only in compression. Eventually, it can break, and from that moment on, you have the standard DEM. That's what we call, in general, the bonded DEM. It's useful to model things like concrete or just solids that break and roll, and so you have this big displacement, rotations, and everything. You have contact, you have everything, but also you have the behavior of a solid before it breaks. Like, we can break solids, and after that they break again, etc. So you can model crushing, etc. Those are some academic examples. And the thing is that we had Fortran DEM codes at SIMNE previously. At 2010, we started coding a version of the DEM in the Kratos multiphysics framework. Then we did our first DEM computations. After that, we validated it, we made some corrections, and then we started with the bonded DEM. That's when I went to Denver and found out that Professor Feng was very critical with the continuous solids simulation. That was the trigger. That made us question some things going on in the bonded DEM. And what are some questions that we have before that time? We were questioning, can we compute the stress between two particles that are bonded? And if you can find in the literature many papers and books that say that you can compute the normal stress as the normal force divided by the area, the contact area, or the tangential stress as the tangential force divided by the area. But if the answer is yes, will the crack initiate in a solid when the limit stress is reached? And imagine we have a solid, this is a big solid, and we put it under limit stress, tensile stress, and basically that's the only bond that would break because you can capture the stress in the same direction that is the macro stress. The other bonds may or may not break. You don't have the guarantee that they will break. But on top of that, if we take the same solid and we put we draw the stress state in as a Morse circle, here you can see it. That's the yield surface for Moore Coulomb. and it's touching because it's the limit stress. The circle is tangent to the lead surface. But if you add some compression in a different axis, then you have a different Mohr circle. However, the DEM is not aware of that other stress in a different axis. So these questions were coming to our head constantly. How can we reproduce these complex stress states if two spheres are not aware of what is happening around them? And traditionally, after some calibration, you can find many publications that say that some combinations of the normal stiffness and tangential stiffness can yield the correct Young modulus. You can also find that combinations of the normal stiffness and tangential stiffness can yield the correct Poisson's ratio, but only within a certain range, okay? And also you can find that you can also reproduce the shear modulus. However, do these combinations that you find by calibrating work for any particle packing? And when I say particle packing, I'm talking about Cartesian packings, stagger packing, random packing, or any packing of spheres you can imagine. And in our experience, the answer is no. And those combinations of normal stiffness and tangential stiffness can reproduce simultaneously the correct Young's modulus, Poisson's ratio, and shear modulus. I mean different tests. So you do one test for Young modulus and check it, and with the same calibration, you try a different test to measure the shear modulus. Does that work? And the answer, in our opinion, is no. And is a structure made of trusses, because the bonded DEM is actually a structure made of trusses, does that behave equal to a continuum? And our answer is that no, and probably calibration is not possible. So you can reproduce some states, but not all of them. So after that, are there any good news? And we think that after the elastic range, there are very good news, because the advantages of the DEM appear at this stage. You can have multi-cracking, and after the cracks, the contact and the friction are detected very easily, and it works very well. The broken pieces can be tracked with large displacement, rotations, etc., and you can add plasticity, damage, whatever you want on those bonds. So we should solve elasticity as best as possible. Of course, the cracks might have started at the wrong points due to a pure accuracy during the elastic region. Now, I will talk a little bit about the traditional approach to the bonded DEM, elasticity plus the rest. And then the first idea I want to give you is the calibration-free approach for the linear elastic range. And the second idea is a new known local approach for the non-elastic range. That means after the end of the elastic range. And finally, I will show some examples, and I will try to explain our experience about that. So traditionally, we have two spheres. We have a contact area marked in red. That's a 2D simplification. And many authors, like ourselves in CIBNE, chose this equation of elasticity, which says sigma equals Young modulus times the strain. And then you substitute, and can you see? Yeah, pointer can be seen. Finally, if you do all the substitutions, you get that the normal force is a constant, that's the normal stiffness, times the relative displacement, normal displacement. Very often, you need to modify the Young modulus, or if you're using a normal stiffness, get the proper macroscopic Young modulus. And what about the tangential force? Well, the first guess would be to use a tangential stiffness, which is the ratio between the shear modulus and the Young modulus times the normal stiffness. But when you have a random packing, for example, and measure the lateral strain, best results are not obtained for that, expression, but for other expressions where you have to adapt a little bit a coefficient, and then you finally get the correct Poisson ratio. Watch out, because modifying the tangential stiffness can change also the elastic modulus, because there is some vertical component of the tangential forces, and then you're modifying the vertical stiffness. So that's dangerous. Now, what did we do to solve these problems? Okay, first of all, we realized that the normal force strongly depends on A, the area. So if you choose a contact area which is bigger, you'll have stronger forces. If you choose it smaller, you have smaller forces. And the thing is that if you draw all the areas, you choose two big areas, you will have overlaps. That means that you are considering that portion of the domain several times. And if you choose small areas, like there, then you have gaps. That's like a porous media. And we're trying to mimic a continuum right now. So the idea is that the ideal solution would be like this, to have some areas that are touching, but they don't have overlaps or gaps. Even if you have indentations or you have separated elements, you need those areas not to have gaps or overlap. And our proposal is to use the weighted Voronoi diagram, where all these areas are not overlapping, and you have basically a partition of the domain. We can also use a cheap approximation. That's where we're using particularly to reduce the costs. But conceptually, the idea is the same. Try to use these areas as the area to compute the elastic stiffness. Now, if you use this scheme and add the weighted Voronoi diagram to compute the areas, these areas, if you use a random packing, you'll still get a wrong Young modulus, because it still depends on KT, and a wrong Poisson's ratio. But if you use a Cartesian packing, that's good news. You get the perfect Young modulus. That's some beginning, and still a wrong Poisson ratio. So let's work on that red square. And the idea is to change these equations, and instead of using a 1D elasticity equation, we will use a 3D elasticity equation, because it's a 3D problem. Now, if you do the same substitution, exactly the same step, you end up with a formula that tells you that the normal force between two spheres is something which is in the traditional DEM plus an extra term which depends on the stresses in the surroundings of that bond. And how can we fill that term? Well, the stresses are known. I mean, traditionally in the DEM, they have been used to plot results. We have seen many talks in the particles conference, previous particles conference, where people draw the stresses. So our idea was to use those stresses to feed that term. And of course, you have to project it, because you have to add the stress in this direction and the stress in this direction. So the global stress tensor, you have to project it to these directions using these formulas. That's only a projection in those directions. So you can fit the extra term that you have on top. Okay, when we did this with a Cartesian packing, we recovered the correct Poisson's ratio. That's the first time I see that, because usually in order to get some Poisson ratio, some lateral strain, you need to have always some random packing, or at least staggered packing. But that's done with the Cartesian packing. I mean, they are columns or spheres, and they are still expanding thanks to that term. However, for the random packing, we are still depending on the tangential stiffness. So we are getting a wrong Young modulus and a wrong Poisson ratio. Well, let's do the same then with the tangential force. We take the equations for linear elasticity for the tangential stresses, that's the expression of the continuum, and we do the substitution. Here we have that the forces in the lateral directions are some AG, and the two derivatives we are substituting in the same fashion that we do for the normal direction, and we need this term, the last term, these two at the end of the formulas, that they are basically a measure of the shear strain along the bond, which is something that you cannot get from two spheres. That's impossible. So we feed that with the information coming from the stress tensor. It's the same idea. So there we substituted those derivatives. Here is marked. Those derivatives are substituted by an expression which uses the stress tensor, which has a lot of information from the surroundings. When we did this, we used the expression for the normal force with the extra term and the tangential forces with the extra terms as well. And also, here we realized that the Kt, so the tangential stiffness, is not changing, it's fixed with the value of Ag divided by L. Then we achieved what we wanted. A good result for the Young's modulus, Poisson ratio, for any packing, basically. Random packing, Cartesian packing, and staggered packing. Those are the tests that we did in the publication. And we can see here, for example, that, let's see if the mouse works well. Yeah, this error is what you get when you use the standard DEM, 100% of error. But if you use the extra terms with Cartesian fine packing, you get only 1.5%. For staggered packing, you go from 43% to 0.4. And for random packing, you go from almost 30% to 3%. So there's still some kind of heterogeneities that are putting some error, but at least we were very happy that we could capture those elastic properties without calibrating. So basically, you put the Young modulus, the Poisson ratio in the formulas, and you're capturing the correct behavior in the bonded DEM. Are there problems? Yes, there are problems. The stress tensor is well defined in the interior of the solid, but it has big errors on the skin because it's based on the divergence theorem, and you cannot do the whole integral in the surroundings of one sphere, which is in the skin. So you have to extrapolate it from the inner particles, or you have to calculate the stress tensor in some other manner. So skin particles are problematic. Some kind of heterogeneity can appear, though that 3% error that we have. And it has, of course, like most DEM simulation, a large CPU cost compared to finite element, for example. Now, the second idea is about the non-elastic range. And usually, for breaking the bonds, we use the local approach. That means combinations of the forces of the local stresses at the bond, and you compare them with the limit. For example, you compare the normal stress to a limit stress, and if that's bigger, then you break the bond, or a tangential stress, or a combination of both, and you can add damage plasticity, fracture energy. Those things can be added to the bond, and that's pretty useful. However, our idea is to use typical yield surfaces from the continuum mechanics. For example, Rankine's yield criterion. And our proposal is to use a non-local approach. The full stress tensor can be used. We have it. That's the formula that I put before, and that's the formula, the value that we are feeding into the forces formula. So you have the stress tensor. You can compute the principal stresses. And with the principal stresses, you can assess if you are inside or outside the yield surface. Those are two different expressions of Rankine with a limiting compression, with a limiting tension. But the thing is that with those principal stresses, you can say if the bond is breaking. And this is a very simple idea, but if you put the solid under limit stress, all bonds should break at the same time, regardless of the orientation of the bond. We said at the beginning that orientation was important when you're using local stresses, so the information along the bond. But here, in this case, you're using the stress tensor, which doesn't care about the orientation of the bond. So all of them, apart from the heterogeneous that could appear with the heterogeneity, all of them can break at the same time. Those are some validation tests we did with uniaxial compression strength test, the Brazilian test, and the shear test. And the results were quite good after calibrating just one parameter. For the UCS and Brazilian test, we only needed to calibrate one parameter. Elasticity was done correctly, automatically, and the limit stress for the Rankine yield surface had to be calibrated, and after 3 or 4 attempts, we got it. However, this is a bare frictional case, and we had to calibrate also the friction between particles, using exactly the same value for sigma ft that we were using for the previous calculation. That was very good news. But we said, okay, if we can do this with a Rankine yield surface, why not more Coulomb, Drucker-Prager, Tresca, von Mises, whatever you have used traditionally? Well, we tried more Coulomb, and the concept is the same. You have this yield surface, you have the stress tensor at the point, you take the principal stresses, you can operate with them and assess if the bond is breaking. Then the same thing. Bonds are breaking regardless of the orientation, and those are the results comparing with experiments for the same 3 tests. But here we had to calibrate 2 parameters, C and phi, for more Coulomb, and a third one for the friction of this case. Does this have problems? Yes, also. The skins are still problematic. Heterogeneity can appear. We could not add damage or plasticity to this approach so far, and it has a very large CPU cost here. So can we apply this to the problems where we have highly cohesive materials involved, like rocks, concrete, or sandstone, whatever? Okay, our proposal is that we have 2 options. We can use DEM as a discretization method, like we said, like it's equivalent to a Voronoi tessellation. And then particles are just a partition of the domain, usually a lot bigger than grain size. I mean, you can have particles of the size of 10 centimeters when the real grain, the actual grain, is 1 millimeter. It's usable for continuous materials. And this method is used to detect formation of evolution of cracks and beyond, the contact, friction, etc. And the second option would be a different approach where you have particles that have the actual size found in rocks, like, for example, sandstone. And you replace the Hertzian law, which is the most known law for DEM, by linear elastic springs. The good thing is that then you avoid the calibration for the elastic range. So this is one option also that we also propose. For option 1, for example, this is a 3-point bending test of a concrete beam, and you can see how it's breaking. Here we used automatic calibration for elasticity, and we used more Coulomb's yield surface. Here we have an example of a ship, which is an icebreaker, and we added some buoyancy to the spheres. You can see how there is certain thickness of DEM, that's bonded DEM, and here the breakage was assessed by a more local approach. For the option 2, where the size of the spheres is the same as the actual grains, we developed the parallel bond method, which is a known method already. It's published and is also present in some commercial codes, which is based on parallel phases of DEM. On one hand, you have unbonded DEM, which is the skeleton. Rocks are touching to, the grains are touching with each other. And on the other hand, you have a bond on top of that, which makes them cementitious material. And if you do that, you can add also the concept of fracture energy. And we did some triaxial tests. This is not the scope of the talk, because the scope was to transfer the ideas to you of what I said. But we have here a shear band where we are using high strength limit and a certain fracture energy. But if you keep the same fracture energy and decrease the strength limit, then you don't have this shear band, because the material gets very ductile, very like chewing gum, say. This is an example of option 2. This is a ring made of sandstone, which is coupled with an FEM simulation. So these particles are glued here, so they are moving with the same displacement exactly. And we are compressing the whole domain from the finite elements and try to see how much of this ring is broken and detached from the ring. And breakage is only assessed looking at the bond. Here we are not using the stress tensor for the breakage, but we are using the stress tensor for the elasticity. So elasticity is calibration fee, let's say, and we have here these chunks that are leaving the domain, this chunk which is almost leaving the domain, and there you have the bonds that are reaching the limit. So these are basically the conclusions. This bonded DEM solves problems which other methods cannot. The bond breakage can emulate micro cracking. The cracks can develop, join, bifurcate naturally. Then you have contact. Then you have friction. You can add as many parameters as you want, like the rolling friction, rolling resistance. Material heterogeneity can be applied easily. You can change the properties of each particle. Broken pieces can break later on. That would be the crashing effect. And we can limit calibration effort to FEM standard. That's probably the main idea I want to transmit. On the other hand, we have the problem with the heterogeneity that can appear when unwanted, because the packings can be very random. They have defects, they have pores, they have voids, and also a very large CPU cost. Not due to a big number of particles, which is true as well and can be solved with supercomputers, but the problem that we are facing most commonly is the small time step. We have very rigid materials, we have very small particles, and the time step is getting really small. So for us, this is the worst problem of the DEM. The rest, we are very happy with that. So use at your own risk. And that's all.